Welcome to the webinar. We are now in Delft in the Netherlands with an audience, live audience. That's nice. The next hour we will spend some time with the international audience that is online to go through one of our main products of the FAST project. I will start very quickly by introducing the project to you. Then we will guide you a little bit through the MIC viewer. The science behind all of this will be explained by two of my colleagues. One of them available in Cambridge, the other one here in the room, Daphne van der Wal and Iris Müller. Then we will go into some advanced applications and services that we can provide, and then a question round. First, let's have some idea about nature-based solutions. We think nature-based solutions are defined by solutions that use ecosystem services to deliver adaptation or mitigation to problems related to, in our case, too much water or not enough water. And of course, there are other nature-based solutions, but from the Deltares and FAST point of view, it's about too much water and not enough water. And we think that these nature-based solutions have a potential to mitigate climate change, and especially concerning the hydrometeorological effects of climate change, meaning the more severe storms that were already introduced by Vegetation half an hour ago, and especially focusing, for instance, on the coastal zone. The nature-based solutions encourage, and that's the idea of a nature-based solution, encourage preservation and restoration of ecosystems and ecosystem services. It's not only about designing an engineering solution, but it's also about restoring a functioning ecosystem that provides a service as part of a flood risk solution. Anyway, nature-based solutions are not new. We use them already for many centuries. Salt marsh restoration and salt marsh creation works have been executed in the Netherlands already for 800 years and are part of our history, about our engineering understanding and toolbox, and are part of nature, because many of them are now Nature 2000 sites protected by law. And if I go forward, from the EU is recognizing this importance of nature-based solutions too. This project that we are talking about, FAST, Foreshore Assessment Using Space Technology, is an EU-funded project. And this project is focusing on creating more proof and demonstrate the benefits of nature-based solutions in comparison to traditional engineering solutions. And we try to deliver in this project some tools that professionals can use that are validated and calibrated, and that deliver quantitative information on the contribution of a nature-based solution to a flood risk reduction solution. And we do that by providing some key parameters, such as the wave reduction produced by a nature-based solution. And in our case, it's about that coastal zone and the foreshore in that coastal zone that is delivering that benefit. And this is one of a number of projects who is focusing on that topic. FAST, you could say the sister project of FAST is called RiskKit, and RiskKit is one of the projects that's looking more inland, behind the dike, what is going on after this wave traveled over the salt marsh or over the coastal zone, and how it is then creating an inundation effect and economical damage. So we will try to interact with you here in the room and in the world. You, as far as I know from looking at the statistics, 51 people from 51 countries have enlisted for this webinar, and we will now try to get to know you a little bit better by getting you active and serving to menti.com and using a code that is asked on the smartphone. When you have arrived at that website, menti.com, use 448921 and fill in a question that is asked to you, where are you from? Where are you working or where are you living? Go to menti.com, use the code 448921. And now I am serving to the website. This is what you will see. I expect a nice bunch of countries now coming up in this word cloud. So the larger the word is, the more people are coming from that same country. So I see one from Wales, I guess. Netherlands is still leading. Spain, there are more from Spain. Bangladesh. Brisbane from Australia. So coming up, menti.com and use the code 448921. Let's see where you are coming from, guys. Or the audience, there must be more than 50 people listening in, I guess. Yeah. Thumbs up, we have about 100. Julia? Not yet. Okay, so this is to keep you happy a little bit. You can keep on filling this word cloud. I will go back to the presentation and I will come back with one other question in the end of the webinar. So this was like an exercise, getting you aware that this is going on in the meantime. So keep filling in your countries. We will check in an hour how much we got. Back to the presentation. The FAST project. The FAST project is aimed to develop a Copernicus downstream service. And Copernicus is the new satellite program developed by the ESA, the European Space Agency. And it has launched a number of Sentinel satellites. And what we are trying to do is use that Sentinel data and produce value with it. And we are focusing in this FAST project on using that Sentinel Earth observation data to parameterize foreshore and floodplain characteristics. And we are looking into morphology, into sediment characteristics, and into vegetation properties of these foreshores. And from that, and for that, we built the MI-Safe package, which is an online viewer, and which is that delivers the number of services for users. And being at Deltares, we have been doing that in an open source and open data manner. Of course, the aim of that is to share this information as much as possible with users all over the world and stimulate the users to take up that information, download the maps that we have provided, and make the next step. FAST is almost done. We are in the end of 2017 and in the last months of this project. In the FAST there are 5 partners involved. I already talked about that. And a number of these partners will have a presentation from Cambridge, Iris Muller, from the NIOC, Daphne van der Wal, but our Spanish and Romanian partners from GeoEcoMar and Cadiz are listening. I will quickly move now to the MI-Safe viewer, which is online. I will show you it in a minute. Guide you a little bit through the online viewer to help you understand what is available in information. Analyze storm search, flood risk reduction, vegetated and non-vegetated bare foreshore. And it download data and access wiki portals to extract more if you need that. And it's part of the FAST project, of course. time to calibrate one part of this webinar that field data, the way how we got to this field data and collected that will be further detailed. And if I click something should happen. I have to go to the keyboard. Oh my God. No. I'm sorry. So, back where we were. We use the model XBeach to produce results based on the global data sets that we have collected in the MI-Safe online tool, which I will go into in a moment. We call that the global data set, we call that the educational modality of MI-Safe. It will show you on any place of the global coastlines, show you a bathymetry. It will show you a storm surge water level. It will show you a transect, which is the line on the left-hand side you see in this picture, and that line is corresponding to the bathymetry shown in that little graph. And it will show you in the right-hand graph, in the graph below on the right-hand side, how much wave reduction is being produced by a foreshore and how much the vegetation is adding to that wave reduction on that foreshore. So the results are coming from a lookup table of pre-computed values for those typical situations, to be quick and responsive in our viewer, and we use a library full of model runs, sort of covering the whole scope, the whole scope of the ranges of all possible variables that we expect to occur on those coastal, on those worldwide coastlines. So let's go to the viewer. The viewer is here presented from as a slide. It has a number of different aspects. It has layers that you can click that will then be activated in the main window. In this case, it shows you an intertidal elevation layer, and it shows you a vegetation layer where the vegetation is found. It can show you in much more detail information on the study sites of FAST. It shows you a location search box where you can go and search your own place. In this example, I went to the Benin coast in Western Africa. It shows you a legend of the layer that is shown in the main window. It shows you a meta link from that layer where you can go and to the geo server where you can dive into the metadata of that layer and start downloading it if you want to. It shows you that line again, that transect. You clicked somewhere, we clicked somewhere on the coastline and the transect is generated, and it generates, of course, this result box and the tabs in that result box. In the previous slides I showed you the impact and the conditions one, but we have three more: the confidence, the context, and the sensitivity result box tabs in the result box. It shows you an issues form link. If you find some issue somewhere on a coastline which you think is erroneous or otherwise, you can contact us, and we will try to help you out. And you can join the community. We have three different ways of joining the community: through the tweet, through the Facebook, and by filling in a community form, which delivers you more interaction with the FAST team. So let's go to the live interface. I'm now online. I will go to show you a little bit about the educational global version of this MI-Safe online viewer, and to help to demonstrate how these natural habitats, coastal habitats, play a role in coastal protection. You can read all this stuff on your own later on. I will continue by agreeing to our requirements and then going down to continue. Here we are. We are now live in the viewer. Here you can see information on the science behind, which will be explained later. The value of which will show you something on our services. And this one button, the use of, will show you a movie how you can navigate through our interface. I'm pointing you to this vegetation present. Tick marks are cross, and contribution to wave attenuation, tick marks and cross. In a moment later they will be colored on and give you some indication of if the vegetation is playing a significant role to wave attenuation on the coast you selected in the world. I will go to the data layer now. Let's go. You see all kinds of folders. I can open, for instance, the FAST global imagery, and now close it again. I can go to, if I reduce the size of the screen a little bit, I can go to the global maps, which are, for instance, containing the wave heights and the storm surge levels that for all coasts of the world that we have included here, and you can find through metadata what kind of information we are using. For instance, I now click the metadata level, the geo server, the geo network server, and you can browse to this information to see what we are using. Already you see some colors. This is the tide and storm surge legend, which gives you some information on where the high tides and low tides are in this on the world. So let's zoom in, for instance, to the Benin coast, where I was in the a moment ago. I think I made a typo there. It happens. Not often. I'm a very good typer. So let's see what we get if we go to this coast and, for instance, ask for a model result. So what you see here is that here on the left-hand side, the vegetation is present, and that the vegetation contributes significantly to wave attenuation in this place. You see the conditions result. It gives you information on. I will move it a little bit to the left-hand side and move this a little bit to the other left. You see the conditions tab. You see different colors. You see that there is the green. Some green here, that is the vegetation. You see the light colored bar, that's the part of the transect that we use for the calculations. You see on the impact tab, the incoming wave height at 100%, the reduced wave height for a bare foreshore, and it's the one that is remaining, including the vegetation on that foreshore. If we go to the data tab, for instance, and now switch on the global imagery, I will increase it a little bit because it's almost unreadable for me, but it could be that it is my eyes. Now you are getting the information on the intertidal elevation map on top of that, and the vegetation presence on top of that. And I can move it around to show you where the vegetation is and where the intertidal elevation map, what intertidal elevation map shows you. I'm now zooming out. So this is basically where we are with our educational viewer modality, we call it, and it will also show you that the confidence of the different layers that we use, which will be explained later, the different information layers that we use to produce this calculation are variable in confidence. The bathymetry is a medium quality, and that means that we are not only using the global, for instance, HEPCO bathymetry data, but that we have added the intertidal elevation data to that. And storm surge and waves are global data sets and are therefore not very precise. The vegetation presence is coming from Sentinel data in 2016, so we are quite sure that we have a reasonable idea of the vegetation presence of this area. The properties are average properties extracted from a database of vegetation properties of a limited number of vegetation types that we have been collecting. So overall, we think this is a medium quality result, and for every place on the coast, this result will change. And in the context tab, you will see that we think we have a foreshore here which is about 500 meter wide, with mangrove growing there with a very low slope, 1 meter slope per almost 1 kilometer width. The incoming wave height is 1 meter, which is the incoming wave height, but it is reduced to 0.3 meter when the foreshore has done its work, including the vegetation. So this information shows you something about how this is related to the crest height of a virtual dike, which we put in our calculation on the backside of the vegetation, where the transect ends, and this gives you an idea what kind of crest height, what kind of dike you need to stop this kind of 10% probability storm surge level. Of course, we are interested in other storm surge, for instance, in 100 years and 1,000 years, but we are not giving that information for this global educational modality, because we think that will give you the quality is not that high of these global results that we will give that as a standard output for this educational version. It can be, of course, it is available, and it can be obtained if you start interacting with us and as part of our services. So to conclude this presentation, I will click this away. I will again show you that we have a science behind tab, which is all information accumulated in this wiki, which you can access. And that, I think, will conclude my quick presentation, guided tour on the educational version of our MISafe online tool. Let's go back to this PowerPoint presentation and move on to the science behind.
Yeah, this should work. Is it working? Yeah. I'll keep it in my hands here. Okay, so we got Sentinel images, multispectral images, 2 in orbit with a 5-day global revisit now that gives us information on the land and coastal waters. They have 13 spectral bands, which you can see here. So they give us information in not only the red, green, and blue, but in many other different spectra, which enable us to define well which sort of surface characteristics we can see on the surface. We also make use of the NASA USGS Landsat missions. These are a little bit coarser than the Sentinels. They're 30 meters rather than the 10 to 20 meters of the Sentinels. They have a big advantage in that they have been launched since the 70s. So there's a large archive of data available, which we can make use of when studying long-term changes in salt marshes and wetlands. In this talk, I will give an overview of all the geospatial data products that are available in MISafe. These are the global geospatial data products and also the local products. And for the local products, we focus here particularly on the 8 case study sites. So the sites in the UK, 2 sites in the Netherlands, in the Westerschelde estuary, 2 sites in Spain, in Cadiz Bay, and 2 sites in the reed beds in Romania. Well, first of all, there's water level and wave data available. These are existing information, and we'll show you that in a minute. We also focus on elevation data, both existing data and data made especially within the FAST project, and then vegetation data, again, available and developed within FAST. So to start with global water levels and wave data, there's the global tide and surge model, which gives us information on extreme sea levels, recurrence probability. There's also the nearshore depth, the limited waves available, and these are all available globally. For elevation, there's SRTM data, which gives us information on the land on a very coarse scale, worldwide. Which we then complemented with JEPCO data, which is bathymetric data of the oceans. So both information on the land and on the oceans, but on a very coarse scale. We also have more detailed information, for example, laser altimetry data for the intertidal area, bathymetry data for the subtidal area. But these are not available everywhere in the world. Well, locally, you can then think of more field-based approaches, like using drones to gather information on elevation. But again, that will not cover the whole world. And this is where FAST comes in. This is a method to derive information on intertidal elevation from anywhere in the world where there is a tide, using satellite information. And it uses global data from a long period of time. So collecting all the data from Landsat and the Copernicus Sentinel-2 in Google Earth Engine. And with this whole stack of data that you have all around the globe, you can calculate a water index for each image, which is then averaged per pixel. And from that, you can get an inundation probability. And you can then scale that using global information on the lowest astronomical tide and the highest astronomical tides to derive an elevation. And this is a method developed by Ed Morris. We'll give an in-depth presentation on that later this morning. You can see two examples of that here in Cadiz Bay, so elevation relative to mean sea level. Also in the UK, in Tillingham. And this was validated in the fields in Spain, the Netherlands, and the United Kingdom, using in situ data of elevation, here the GPS data of elevation, also information from the drone, structure for motion data from UAV, and also airborne LiDAR altimetry data. And you see if you plot the predicted one from the satellite against the observed one from the in situ data, that it worked quite well. And there's some more validation there, also with airborne LiDAR against the satellite-derived intertidal elevation for sites in the US. And you can also see that that matches pretty well. Again, this is valid for areas where there is a tide. So we didn't show the Romanian site because there's no any tide there, so that wouldn't work there. Next is a reclassification of the Korean dataset, which gives us information on vegetation type. So we can distinguish, for instance, forests from marshes here. And then there's information on vegetation presence, also done in the Google Earth Engine and available for the whole world along the coast. Again, well, this is a whole stack of data, in this case Sentinel-2 data from 2016, from cloud-free pixels of every image along the coast, where a vegetation index is then calculated for each image, for each pixel, It's then averaged, and the amplitude is calculated, and from that a sort of threshold is applied depending on the seasons to determine what is vegetation and what's not, and then a global vegetation presence map or presence absence map is then produced. Well, the vegetation is not static, it can change over time, and this is where the Landsat series comes in. This is a method based, again, on a long time series of images, but here using data from the 80s and comparing that to data now and looking at the change in vegetation presence, also done in the Google Earth Engine, and you can see then where vegetation has gained area and where it is lost. In this case, in Tillingham, you see at the edge, there's a lot of red there. That means that the cliff has retreated there. Well, I already mentioned NDVI, so the vegetation index. We also have that as snapshots, which you can see here on the left for Cadiz Bay. The greener, the more vegetation, more biomass, the healthier the vegetation. And negative NDVI means water. So the blue areas are water. And on the right-hand side, you can see Romania, and you can clearly see that these are the reed beds. They have a much higher NDVI than what you see in Cadiz Bay. You can also look at that seasonally. So we see a time series of winter, spring, and summer there, which we also validated by looking into the field with the spectroradiometer and calculating an NDVI from there. Well, finally, we calculated leaf area index of the marsh, which gives us more of information on the structure of the vegetation. It's the one-sided green leaf area per unit ground surface area, again from Sentinel-2 images, and then only for the areas that have salt marsh there. And you see two examples there, again from the Romanian reed beds in 2 seasons in time. And with that, we come to the field measurements, which is presented by Iris Muller, and she's online, hopefully.
Okay. I hope you can all hear me. And let me just find the right slide. So I have, oops. So I have put together a few slides to take you through our field measurements. As you might gather from Mindit and Daphne, our approach to use Earth observation here for an assessment of foreshore properties requires really a full and detailed calibration. And in order to do that, we clearly have to go out into the field and fill in the bottom left-hand side of this diagram here. So we're really achieving a calibration, but also a validation of our model results at the end of the day through getting physical and biological information of the foreshore by being out in the field. Now, depending on your particular interest in the coastal environment, you clearly might ask different sorts of questions of those properties that one might want to measure. In our case, as we're focusing on wave dissipation, coastal protection type of services, we're really looking at attributes that affect water level and waves. We're looking at what aspects of the coastal wetland give us a clue about its stability so that we can with confidence predict that coastal protection service over time. And we're looking at aspects that particularly lend themselves to be viewable from space. So we need to go out there and we need to measure those kinds of properties to see how well they relate to what we can see from space. As those of you who work in those kinds of environments will know, that's obviously very difficult because when the tide is in, you can't get to those surfaces. And often the conditions there can be quite challenging. So we deliberately selected these different field sites, as Daphne said, to cover a wide range of different types of coastal vegetated zones. And each and every one of them had their physical challenges associated with them in terms of access and gathering data. And at the end of the day, that's why we want to move to Earth observation, right? So that we don't have to traipse out into the mud and get stuck in water. I don't know if you can see this person here outside of the reed beds, but we had to wade waist deep in that water to take our measurements in Romania. So it's not without challenges, but even so, we managed to get a range of measurements. Daphne already referred to the incoming and reflected radiation measurements. We measured various vegetation properties, sedimentary and topographic properties, the water depth, of course, and of course the important thing here for calibrating our wave models is the measurement, the high frequency measurements of waves. Where exactly did we measure these? And that clearly varied within our field sites because of these access and measurement challenges. So you can see from these two sites here a comparison of our measurement plots in the UK. That's about 100 meters here on that scale bar. And then this is the Romanian site, and it's much more difficult to take measurements in the center of the reeds here. So we've had to spread quite a lot of our sedimentary measurements, for example, around the edges. Daphne already also alluded to the fact that calibration is really important when it comes to the remote sensing image use, but also we had, through having all these different field sites, we had to cross-calibrate our instruments to be used simultaneously at these different sites. So we really were aiming for a systematic and standardized approach across all different sites with instruments at the same time, deployed seasonally over the periods of a year, and therefore cross-calibration was absolutely essential. So that the quality of what we produce is really quite high because we went through a lot of effort to cross-calibrate our spectra that we measured in situ on the ground. And here you can see the results from just a cross-calibration exercise that we did in the UK with all the different instruments from the different institutes. That, of course, allows us then to go out into the field and get as accurate as possible a ground spectrum from which you can then cut the individual bands and the reflectances of the wave bands that correspond to Landsat or Sentinel-2 or any other Earth observation platform. And with that, we can then look at NDVI derived at different parts of the year and look at seasonality and so on. So we pick up seasonal changes directly through quadrat measurements, and we sampled vegetation. We measured the biomass here in the top plot in grams per square meter directly, and we were then able to relate that to the ground-based spectra, and then we were able to relate those to the Earth observation data that we had. So really a lot of what we did here was about quantification of temporal variability as much as a calibration of the whole method in and of itself. And the temporal variability, of course, is important not just with respect to vegetation, but also with respect to surface roughness on tidal flats. And so we deployed some quite innovative techniques to look at the roughness of vegetation with a particular biomass by using side-on photography, but also the roughness of the tidal flat itself by using side-on photography against a calibrated board. And you can see in this plot on the bottom right here that across our different locations, our different coastal environments, we can really see a great difference in that kind of roughness. We deployed a drone to get this bed roughness at the larger scale configured, and Daphne's already talked about that, so I won't spend a lot of time on that. and we also deployed quite a lot of instruments that look at different timescales of bed elevation changes. So in the bottom right here, we're installing a sedimentation erosion table that measures elevation change over a period of a year and more, and therefore allows you to kind of relate the geomorphological performance, if you like, of that coastal area in relation to things like sea level rise and sediment availability. And then on the left here, you can see an SD sensor, which measures the sediment dynamics over a much shorter timescale of individual tidal cycles or series of spring and neap tidal cycles. We also spend a lot of time to actually map, in terms of mapping the topography, and you've seen some of that data in Daphne's slides, but in terms of validation of the EO, the Earth Observation Derived water level method for getting a more accurate digital terrain model. Over the longer term, of course, we're interested in how all these kinds of topographic measurements relate to the stability of the coastal wetlands, and we can put them all together, these short-term measurements of sediment accretion, for example, with longer-term measurements of elevation change. And you can see at the bottom here the elevation change bars for the different countries. And we get very different responses in very different systems because the localized setting is clearly key. And that explains in part why the educational version of the MySafe viewer it has to remain quite general, because a lot of effort needs to go into calibrating it at the local scale and for more specific questions. Another thing that's possible when you start to go more local is you can use regional or locally acquired airborne Earth observation, for example, LiDAR imagery, and you can look at spatially explicit features on coastal wetland margins, and from that you can try to get a picture of what the response might be of those margins to sea level rise and increased storminess and things like that. So that brings us to the hydrodynamics, which is of course important for our project when we're looking specifically at coastal protection. And we deployed a telemetered system of wave recording pressure sensors that are bed mounted, and they were mounted along a cross-shore transect at various positions along the shore, and then allowed us to get wave spectra for a wide range of different water depth conditions and wave heights. So when Brechtje was talking earlier, before we started the webinar in Deltaris, she was mentioning that actually we have very little data in extreme water depth conditions so far, and we have very little data of a range of wave heights from these kinds of environments. Well, we've filled this gap with our data to an extent in terms of the field measurements. It's a novel set of field measurements for a range of environments. And we can then look at the picture of wave dissipation in these different environments across these different types of systems, these different types of vegetation characteristics at these different sites. And you can get an idea of that here when we compare, for example, reed vegetation with marsh vegetation. And the reeds clearly are very efficient at dissipating incident wave energy, whereas the marsh, being inundated with a significant amount of the water column still above the canopy, is somewhat less efficient at the bottom half of this diagram. So we can then compare the no vegetation zone of these environments with the vegetated zone of these environments too, to give you confidence in our predictions that you get from the MySafe viewer. And with that, really, it brings us back to our ultimate game, which is, or ultimate aim, which is to have general rules in the predictive model that allow you to estimate the contribution of the flood protection of any kind of coastline. That is not to say that the information that we've gathered and all of that field information and the methods that we're using is also applicable for other kinds of questions you might be asking with respect to the biological and physical status of that foreshore for other applications, such as the estimation of ecosystem services and so on. So before I finish, just I'd like to point you to the MI-Safe part of the viewer, which gives you the information about the science behind MI-Safe. And you can click on that. Mindert pointed it out earlier in this demonstration, and you can find out a lot more detail about these individual methods. And there's also links to YouTube videos that explain how those measurements can be made. And we hope that those will be useful for getting some sort of consistency of how these measurements are made by others across the world. So with that, I'll finish, and hopefully there'll be some questions, and I'll be happily answering them later on.
I should be able to start talking, but I will put the speakers on the headphones. I guess we are in the game again, Julia. Thank you, Iris, very much. I think you can hear me, so the rest of the audience can hear me. Can hear me too. Go to show my screen. Yeah. All right, great. So we will zoom ahead to the I'm sorry, I have to go to the presentation part where I need to pick this up. I think this will be more fast. I think there we are. Okay, Julia.
Ja, volgens mij doet het.
Yeah, it's working. But I need this thing. I need the clicker. What is the? Yeah. Thank you very much. We are going to Iris. Let's continue. I would like to zoom in a little bit on the more detailed analysis that we have been doing for study sites, but using the online tool. Before that, I reiterate a little bit on the inputs that we need to do that. So that is about getting information on the waves and the water levels, getting information on the bathymetry and the topography, and getting information on the vegetation presence and the vegetation type. And that gives us the wave deduction, and we can pick that up to calculate overtopping of a virtual, or in the detailed analysis I'm going to show you a real dike, really existing dike, and that information can be picked up, for instance, by a flood inundation model, which I will show you in a moment online too. How we step through this analysis, I'm not going to go into detail. You have the idea that we start with selecting a transect on a certain coast, and then computing the wave levels, merging that with the elevation and the bathymetry information of that specific location, and then add the vegetation information to it, and then start calculating the resulting attenuation on the toe of the dike, and moving towards calculation the overtopping, and therefore the required crest height to reduce that overtopping to acceptable levels. Bathymetry has been discussed. Wave and coastline data has been discussed. Everything is in the online view. You can look for yourself. Everything is in the folder Global Maps. And what I have been showing you until now. Elevation data have been discussed. Here you can see in the different colors of the graph that some of the information, the darker colors, come from the global mapping that is available, the GEPCO and the SRTM, and other colors, the lighter colors, show you where the intertidal elevation map that the FAST project generated is adding more detailed information. Here is an intertidal elevation map example. The vegetation type is added for a certain area, and the XBeach model starts running. The XBeach model takes this information which has been discussed before, what is about vegetation characteristics, stem height, stem diameter, vegetation density, and that drag coefficient. That is the one that we use to calibrate the results to a certain area. And the vegetation density is the link to Earth observation information, which has been discussed by Daphne, which is taken up by the model as this so-called leaf area index. So there is the link with Sentinel information into the XBeach vegetation modeling that we do. So the model will calculate the effect of vegetation on short waves, on infragravity waves and flow, and on the wave setup, which is of course on this virtual dike or really existing dike in this detailed location. We will use vertically non-uniform vegetation in our detailed schematizations. In the global version that I showed before, it's an average vegetation that we use, but in the detailed one that I'm going to show you in a minute, it is non-uniform vegetation with distribution in the vertical and in the horizontal. Because from the LAE information, the leaf area index information from the Earth observation, you can see that, of course, the horizontal distribution of the vegetation is very variable. So I would like to continue, but I'm clicking buttons and nothing happens. And even here it's stuck. I'm not precisely aware what is going on now. It should get unstuck at some moment. Let's see what happens here. Now it works. Okay, here you can see an idea of a hydrostatic calculation of XBeach, where we keep the water level constant more or less, and you can see how this XBeach is interacting with vegetation. So this type of advanced modeling is available in the open source library of Delft, and which is included into the FAST products. Of course, we can do it non-hydrostatic, which is the most advanced way of working with XBeach, where we follow in detail the wave pattern that is forced onto the model into the vegetation. And you can see that the vegetation is very effective in this example in reducing the wave heights, and it's even influencing the water level. So the vegetation model works of the XBeach, the numerical part of the MI-SAFE interface is calculating the wave dissipation, influencing infragravity waves and flow dissipation, calculating the wave setup, is using this vertical schematization and horizontal distribution of the plants, and is the implementation is variable. You can choose as a user, if you work with this on your own advanced implementation, how to use this advanced modeling for your location. Let's go into the detailed results of one of our study sites. Here you can see how the model is generating a wave attenuation over a transect. The transect is the purple colored one that is active. You can see the green layer on top of the bathymetry showing you where the vegetation is. You can see the dike, the sharp point, which is keeping the storm surge of a 100-year storm event, 1% likelihood at bay, and you can see how the bare and the vegetated foreshores are influencing the incoming wave height. So let me go to the viewer now to show you this live. I will continue. All this information you can find by yourself, of course. I will go to a study site called Tillingham. Here you can see that map that was shown in the presentation a moment ago. I will go to FAST Global Imagery. For instance, show you intertidal and elevation for this part. And then I can, for instance, zoom into this place further. When it is a little bit slow. I think other people are using the same viewer at this moment. Let's go to Tillingham, which is here. I'm opening the folder of Tillingham with all the results for this place. It has, for instance, drone information. It has the leaf area index information. It has a wave height XBeach application, which I will show you in a moment. It has the digital terrain model information. It has all the detailed map layers that we need to do a detailed analysis on this area. Let's see, for instance, if we run the XBeach model, for instance, with vegetation here, and see what happens. I think I have to get rid of this one. I will zoom in a little bit more, and in a moment the model will start running. You see it from here. So what we set up is a XBeach run for a severe storm, which is going to overtop the dikes behind Tillingham, behind the salt marsh of this Tillingham area, which is on the north-east coast of England. And this information is derived from a very detailed, advanced XBeach run for this area. And I have to stop it at a good moment in time. I think, for instance, here you see this is the highest water. You see the waves arriving at the dikes. And if I stop this run and start with the advanced functionality of analyzing what kind of effect this will have on flooding. I am now going to the inundation model, which is picking up the XBeach information from the wave attenuation run-up and overtopping of the dike coming from the sea, and this list flood model is now showing you the inundation of the hinterland based on that information. So basically this is what we call advanced modeling within our FAST project, which we can execute for any coast if we have this type of detailed information on the world. So I was trying to show you also a transect with detailed information, but I think I'm running out of time, and I will go back to the PowerPoint presentation in a moment. Here you see that same place again, Tillingham at the northeast English coast, and with those here it is shown the LAI, the leaf area index, which is of course one of the inputs for the wave attenuation calculation of the model. Let me continue. So what we conclude that we have great benefit from the Sentinel data, which are quite useful for us, and but we do not have that long-term time series yet from Sentinel, so we need a Landsat for that. for instance, see how vegetation has changed in some decennia. We have now these specific algorithms that translate Earth observation information to properties of the foreshore that you can use for these assessments. For instance, going towards this leaf area index and translating that into vegetation parameters that go into the XBeach model. We have a good potential to analyze on the local scale in detail, on the regional scale and global scale in less detail, challenges related to flood risk reduction. And for instance, this intertidal elevations map is in that sense a great step forward, because this is a gap in the data that was filled in this project. Time series analysis has been shown to be quite interesting based on, for instance, this vegetation change map. And I will repeat, we can generate advanced outputs for disaster risk reduction by adding other Earth observation sources or other modeling tools. I showed you list flood for the inundation exercise to focus on specific coastal challenges that are of interest to a specific users. So, in a sense, we are just starting on this exercise, and the data are now streaming in, and we are quite interested in getting a link to you and you joining our community to make that next step. That's why we try to do this, of course, open source and open data. Let's make a little excursion to where we want to go. The MIC viewer will be online for a long time because it's embedded in the Deltaris open source systems, and we will maintain that the coming years. We will provide that educational service for free as it is online already. We will, you as a listener or a user can take part by joining our community. And of course, we hope to work in the advanced level on specific sites to get a little bit more interactive with users to advance our maps, to update our maps, and to add functionalities to this FAST product packages. And of course, again, I would like to focus you on the Join Community Fund. Okay, we envisage a number of services that we can deliver to you in this project. There is training available. For instance, today in this Delft Software Days, we will execute such a training and work hands-on with interested users to better understand what is possible, what the possibilities are to work with this interface and what you can develop on yourself for a specific site. We can link to the open source databases, and you can use the open source models. Of course, we need to interact directly with you to further develop these advanced services. And that, of course, will be a personalized interaction with our FAST consortium if you want to embark on that track to help you apply this kind of information for your own local part of coastline.